I will now be sharing the slides. So is the screen visible?
Yes, ma'am. It is visible.
Okay. So let us start our feed-forward neural network. So another type of, because we covered in this the perceptron, adeline and medeline in the last class. So another feed-forward neural network is your back propagation network. Now what it does is, the name is back propagation because it tries to back propagate the error. It calculates the error at the output layer and the hidden layer, and then it back propagates that error so as to adjust the weights. So this implements a gradient descent search through the space of possible network weights and iteratively reduces the error between the training example target values and the network output. So that is the desired output and the actual output that we are getting. So again, the almost same training procedure is there, with the difference that error is calculated at each layer and that error is back propagated so as to again calculate the change in weight and change in bias. So because of this feature, back propagation network is more likely to get the optimal solution than other networks, and also it works very well on linearly inseparable problems, unlike the perceptron and adeline models, which were better only for linearly separable problems. So here in this backpropagation network, we have one input layer, one output layer, and also one hidden layer. The number of neurons remain exactly the same what we had studied earlier. So number of neurons in the input layer is the same as the number of features in your data set, and the number of neurons in the output layer is the same as the number of classes in which you want to classify. However, you can vary the number of neurons in the hidden layer according to your problem. So in backpropagation network, the learning algorithm that is applied generally calculates a differential of the activation function, right? So this is very important, that the activation function that you are using should be monotonically non-decreasing and also differentiable, because it is calculating the differential, right? So this is applied to the multi-layer feed-forward network, and all the processing elements here, they are applied with a monotonically non-decreasing and differentiable activation function. The weights here are updated with the gradient descent method. We will be discussing the gradient descent shortly. So this is a method where error is propagated back to the hidden unit, and therefore the name is back propagation. The aim of this neural network is to train the net to achieve a balance between the net's ability to respond, that is memorization, and its ability to give reasonable responses to the inputs that are similar but not identical to the one that is used. That is generalization. So this means that your model should not be overtrained. It should give you good results with the known data, but it should also be able to give you acceptable results with the unknown data as well. So that is what is called generalization. So the training of the backpropagation network is done in three phases or stages. One is the feed forward of the input training pattern, that is the normal training of the network. Then calculation and back propagation of the error. In the phase 2, you calculate the error and back propagate it so as to change the weights. And the last step is final updation of the weights according to the error calculated in phase 2. A backpropagation neural network is a multi-layer feed-forward neural network consisting of one input layer, one hidden layer, and one output layer. So the activation function, you can choose to be anything, but it should be continuous, it should be monotonically non-decreasing, and it should also be differentiable at all the points on its domain. So this is the architecture of backpropagation network. Right, so you see that we have one input layer comprising of neurons x1, x2, x3, and so on up till xn. So we have n neurons in the input layer. Then the hidden layer is there where you have z1, z2, z3, and so on up till zp. So p number of neurons in the hidden layer, y1, y2, and y3, and so on up till ym. So this is the output layer, m number of neurons in the output layer. So you see that here we have two sets of weights, right? V11, V12, V13, and so on. These are the weights for your hidden layer units. Similarly, W11, W12, W13, and so on. These are the weights for your output layer units. Now, in this case, both these weights, the V's as well as the W's, they will be adjusted and updated in each iteration. Now, first of all, let us see the terminologies that we will be using in the training algorithm. So X is your input. So when I say just X, it means a training vector, right? So it is having n number of points, X1, X2, X3, and so on up till Xn. So these are the n number of points that are applied at the n nodes in the input layer. Then T is the target output vector comprising T1, T2, T3, and so on up till Tm. So M points. So that is, these are the values that are there at the output layer neurons in the output layer. Then alpha is your learning rate. Xi is the ith input unit. So since you are applying identity activation function at the input layer, the input and output signals here are the same. So you simply apply the input values at the input layer neurons. Then V naught J is the bias on the jth hidden unit, and W naught K is the bias on the kth output unit. Zj is the hidden unit J. So the net input to Zj is represented as Zinj. So this is equal to V naught J plus, that is the bias at the jth hidden unit, plus summation I is equal to 1 to n. Why n? Because we have n number of units there at the hidden layer. Xi B ij. So this is simple formula which we have done earlier also, that is multiplication of the weight with the input vector. And the output, then to get the output Zj, we simply apply the activation function. So this we have studied in the earlier class also, yesterday also, that to get the output we simply apply the activation function over the net input. Then Yk is the output unit K, and net input to Yk is represented as Yink. Now this is equal to W naught K, that is the bias, plus summation J is equal to 1 to P Zj Wjk. Why? Because there are P number of units in the hidden layer. So the length of J is, the length of Z vector is P. Then the output Yk is calculated by applying the activation function over this net input, that is f of Yin. Delta K is the error correction weight adjustment f, or so this is your error that you actually get at the output layer. So this error correction you apply at the output layer weights, that is your W matrix, right? So this is back propagated to the hidden unit that feed into the unit yk. Then delta j is the error connection weight adjustment for your hidden layer unit, that is the v vector, and this is happening due to an error at the hidden unit. Then this is back propagated to the input unit that feed into the this hidden layer. So commonly used activation functions are binary sigmoidal and bipolar sigmoidal activations, and these functions are used because I told you that function that you are using first of all should be continuous, because if it is not continuous throughout, then it will not be differentiable at all the points. So it should be continuous, it should be differentiable at all the points, and non-decreasing monotonous. Now let us see the training algorithm of bipolar of this backpropagation network. So I told you that the training happens in 3 phases, right? So feed forward phase, error calculation phase, and updation of weight. So 3 phases are there. So first of all, we will initialize the weights to any random value and take any learning rate, some optimal value you can choose. And then you perform steps 2 to 9 till stopping condition becomes true. And then you perform steps 3 to 8 for each training pair indicated by ST. So S is your input vector, T is your target vector, that is the label. So in phase 1, that is the feed forward phase, each input unit receives input signal xi and sends it to the hidden unit, that is I is equal to 1 to n, because we have n number of units in the input layer. Then each hidden unit zj sums its weighted input signal to calculate the net input. So zinj using the same formula is equal to v naught j, that is the bias, plus summation I is equal to 1 to n, because n number of units are there at the input layer. So x vector will be length of x vector will be n. So summation I is equal to 1 to n xi vij, and j will range from 1 to p, because p units are there at the hidden layer. Then you calculate the output of the hidden unit by applying its activation function over zinj. So that will be simply Zj is equal to f of Zinj. And then you send the output signal from the hidden unit to the input of the output layer unit. And then again, when this will go to the output layer unit, you will calculate the net input for the output layer, right? So that is denoted as Yink. So this is equal to W naught K, that is the bias at the output layer, plus summation j is equal to 1 to p, because p units are there at the hidden layer. So length of the z vector is p, okay? So zj into wjk, where k will range from 0 to m, because we have m number of units at the output layer. Then you apply the activation function to compute the output signal. So yk is equal to f of yink. Now each output unit yk, so total units are m, so k will range from 1 to m. This receives a target pattern corresponding to the input training pattern and computes the error correction term. Okay, so this is the error calculation phase, right? This is phase 2. So delta k is the error at the output layer unit. So this is equal to tk minus yk. So this is your error term, right? Because t is the target value and yk is the actual output that you are getting at the kth node in the output layer. This you will multiply by the differential of your activation function, right? So f dash is the first order differential, right? So the partial, I think you know what is partial differential and first order differential. So f dash is the first order differential, f dash yink. So then you update the change in weight and bias. So delta wjk is equal to alpha delta k zj, and delta w naught k, this is your bias. This is equal to alpha delta k, right? So this is the change in weight and change in bias for your output weight and output bias. So then you send delta K to the hidden layer backwards. So each hidden unit Zj, J will range from 1 to P because P number of units are there at the hidden layer. Then it sums its delta inputs from the output unit. So del Inj is equal to summation K is equal to 1 to M del K W Jk. So then the error term del J is equal to del Inj F dash Z Inj. So F dash is the differential of the activation function at the hidden layer. Then you update the change in weights and bias. So delta Vij is equal to alpha del J Xi and delta V naught J is equal to alpha del J. So this is the change in weight and change in bias at the hidden layer. Then you simply update the weights by adding these change of weights and bias in the third phase. So in the third phase, you calculate the final weights. So each output unit Yk updates the bias and weights. So Wjk new is equal to Wjk old plus delta Wk, and W naught K new is equal to W naught K old plus delta W naught K. So this is your change. This is your new weight and new bias. Similarly, for each hidden unit, you update its bias and weights. So Vij new is equal to Vij old plus delta Vij, and V naught J new is equal to V naught J old plus delta V naught J. Then you check for the stopping condition. The stopping condition may be certain number of epochs reached or when the actual output equals the target output. This means error becomes sufficiently small. So this backpropagation network converges since it implements a gradient descent on the error surface. You see that at every point we are calculating the first order differential, right? First order differential is nothing else but the gradient of a curve. Okay, so actually it is calculating the gradient and descending that gradient in each iteration. So it is actually implementing a gradient descent on the error surface in the weight space, and this will roll down the error surface to the nearest minimum error and will stop after that. So this becomes true only when the relation existing between the input and the output training patterns is deterministic and the error surface is also deterministic. So this is not the case generally in real world. So backpropagation algorithm is purely based on the stochastic gradient descent method. We will be saying what is the stochastic gradient descent. BPN may get stuck with local minima and may be unable to find satisfactory solution. So the randomness of the algorithm helps it to get out of the local minima. So the error functions may have large number of global minima because of permutations of weights that keep the network input output function unchanged. This have numerous troughs. Can you please mute your mic? Some noise is coming. Okay, so this is the testing algorithm. So in testing, what we do, we first of all initialize the weights, because in the training algorithm we found out the final weights for both the layers. So initial weights are taken from the training algorithm, and then for each input vector X to be classified, you perform steps 2 to 4. You set activations of the input units to X. Then you calculate the net input to hidden unit Z and its output. So Zinj is equal to, this is your net input, V naught J, that is your bias, plus summation I is equal to 1 to N Xi Vij. Then Zj is your final output. You simply apply your activation function over the net input. So Fzinj. Then now you will apply this output to the output layer at all the units of the output layer. So Yink, this is the net input that you will be applying at the output layer. This is equal to W naught K, which is your bias, plus summation J is equal to 1 to P Zj W Jk. Then you find out the output by applying the activation function over this net input Yink. So Yk is equal to F of Yink. Then you can use sigmoidal activation function for calculating the output. So let us see gradient descent, because this is the method that your back propagation network is applying at each step. So this is the most popular term in machine learning. You must have heard it many times. So this is an optimization algorithm for finding a local minimum of a differentiable function. As the name suggests, gradient descent. Suppose you are standing at the top of a hill cliff, right? And you want to come down. What you will do is you will check your surrounding and you will find the steepest slope, right? The steepest one is naturally the shortest one. So you will find the steepest slope and take one step ahead. Then again at the that point you will again check your surrounding, find out the steepest slope and take one step ahead. This you will keep on doing till you go to the bottom of the cliff. So this is the gradient descent algorithm, which actually calculates the gradient at each step of its iteration and keeps on doing it until it achieves the optimal solution, that is the global minimum. So this algorithm is used to find the values of the function's parameters that minimize a cost function as far as possible. So there is a what actually. So what is that hill cliff? That hill cliff is your cost function, right? So you want to minimize the cost, and how will you minimize? You want to minimize it. You want to minimize the cost and find out the optimal parameters at the same time, which are helping you minimize the cost. So this you do at each iteration. At each iteration, you find out the differential of that cost and the adjust the parameters by finding out that differential. And this you keep on doing till you reach the optimal parameters and the minimum cost. So gradient measures how much the output of a function changes if you change the inputs a little bit. So in mathematical term, a gradient is a partial derivative with respect to its inputs. So gradient descent finds the local minimum of objective function by following the steepest descent of gradient. That is a first order derivative of the function. So it is the first order optimization algorithm. So this is how it looks like. So what you see on the screen is actually a convex function. So a convex function is that function if you draw if you connect any 2 points on the curve with a straight line, then that line will not cross the curve at any point. So such a curve is known as convex curve, right? So what you see on the screen is a convex curve. So gradient descent is mostly used to find optimal minima in your convex curves. So when the learning rate is optimal, if you see in figure A, when the learning rate is optimal, the model converges to the minimum in just one go. You see eta is equal to 1 by c, and in just one go, one iteration, you can reach the bottom point, that is the minimum. Now when learning rate is too small, that is, you suppose the optimal value is 1 by c and your eta is much less than 1 by c. Then in that case, you take some iterations, but you reach the optimal solution. So it converges. In figure C, you see learning rate is higher than the optimal value, right? So your optimal value is 1 by C and eta is a little larger than 1 by C. However, it is smaller than 2 by C. That is smaller than 2 times the optimal value. Then in that case, you will overshoot the point, but slowly converge to the solution. But as you can see in figure D, if the learning rate is very large, that is eta is larger than even 2 times the optimal solution, that is 2 by C, then it overshoots and diverges and moves away from the minima as you keep on performing the learning, right? So learning rate should not be kept too large in case of gradient descent. So this is the curve that you get if you plot. The epoch means number of iterations, right? And on the y-axis, you have the loss value. So if the learning rate is very high, then you see that the loss keeps on increasing and has a very steep curve. However, if the learning rate is optimal, that is the good learning rate shown by a red curve, you see that it as the number of epochs increase, it gradually minimizes and achieves a stability, and so that just to show that after that it won't minimize the loss. So it is a very quite a smooth curve in case of good learning rate. Now there are multiple variants also of gradient descent. So there are three most commonly used variants. One is your batch gradient descent, another is mini batch gradient descent, and third one is your stochastic gradient descent. So the main difference between them is the amount of data that you use while computing the gradients for each learning step. The trade-off between them is the accuracy of the gradient versus the time complexity to perform each parameter update. Naturally, batch gradient descent is the slowest. It is a little bit slower than your mini gradient descent, which is further slower than your stochastic gradient descent because of a lot of computation involved in case of batch gradient descent. So in batch gradient descent, we have to sum up over all the examples on each iteration when performing the updates to the parameters. So if you see, so your cost function is given as j train theta, that is 1 by 2m, where m is the number of training examples. H theta xi is your hypothesis, that is the actual value that you are getting minus yi. So this term is your error. So summation of the square of this error. Now this is your cost function. J train theta is your cost function. So you will simply compute its first order differential. So if you compute its first order differential, it is equal to 1 by m x theta xi minus yi. So this you feed into the updation of the theta. So theta j is equal to theta j minus learning rate upon m. So you have just fed your first order differential. So learning rate upon m into summation x theta xi minus yi into xj. Now this you will calculate by summing it by summing over all the instances. So suppose if the number of instances are n, then you will sum this for all the n instances, and this summing up you do at each iteration. So after summing up, you calculate the new theta. So now you will get the new parameter. Again, you calculate the cost function for this new parameter. Again, you find out the first order differential and update the parameter for all the n instances. And this you keep on doing till you obtain the minimum cost value. Minimum cost, your cost say becomes less than any acceptable cost value, right? So this is costly because you have to sum up for all the n number of instances that you are having. However, to make it a little faster, another variant was proposed, which is mini batch gradient. So what it does is it does not sum up for all the n instances. However, it takes small batches and it sums up the value of this thing, first order differential value over a small batch of the total number of instances. So suppose you can make batches of any number. So here in this example, we have made batches of 10. So for I is equal to 1, 11, 21, because 1 to 10 has been summed up in first iteration. So naturally, the second iteration will start from 11 and sum up till 20. So batches of 10 have been created. And let the summation be the summation from I to I plus 9 represented by k. And again, you have simply taken the first order differential of the cost function. So theta j is equal to theta j minus learning rate upon size of b. Size of b here is 10 that you have taken, that is the batch size, into summation h theta xk minus yk into xjk for every j is equal to theta to n. So if you see in the graph, the batch gradient has a very smooth curve down the graph, right? However, your mini batch gradient is showing many troughs and cones. So this is because small batches have been used rather than summing it over the entire set of instances. Another one, which is your fastest among your gradient descent, is your stochastic gradient descent. So what it does is it does not take any batch at all. It performs the parameter update for each and every instance in the data set. Okay, so therefore your learning happens for every example. So let xi yi be the training example, and your cost is given as 1 by 2 summation s theta xi minus yi whole square. Then your cost function is 1 by m summation cost theta, and then you again calculate, repeat the same steps. Instead of forming batches this time, you are doing it for each and every instance in the data set, right? So if you see in the figure, the blue line shows how the batch gradient descent converges. So it converges very smoothly because all the instances have been summed up to find out the parameter update at each iteration. However, the green line shows the mini batch gradient descent, and it is gradually turning towards the optimal solution. But your stochastic gradient descent has many turns and changes, and takes a roundabout curve to reach that optimal solution. So let us see the convergence trends in different variants. So batch gradient descent follows a straight path towards the minimum. If the cost function is convex, then it converges to a global minimum. If the cost function is not convex, then it converges to a local minimum. So here the learning rate is mostly held constant. In mini batch gradient descent and stochastic gradient descent, the algorithm does not converge but keeps on fluctuating around the global minimum. So in order to make it converge, we have to slowly change the learning rate. So the convergence of stochastic gradient descent is much noisier, as in one iteration it processes only one training example. So this backpropagation network has a lot many applications like load forecasting, problems in power systems, image processing, fault diagnosis, and fault detection. It is having much broader spectrum of applications because it is suitable even for the linearly inseparable data, and therefore finds application in image processing, gesture recognition, speech recognition, signature verification, bioinformatics, and even in structural engineering design. Another type of network in feedforward is your radial basis function network. So this is a classification and functional approximation neural network that was developed by MJD Powell. So this network uses the most common non-linearities such as sigmoidal and Gaussian kernel functions. So the Gaussian functions are also used in regularization networks. And the Gaussian function, if you see, the curve looks like a bell, right, which is symmetric over the origin. So the formula for this is Fy is equal to e to the power minus y square. So when the Gaussian potential functions are being used, each node is found to produce an identical output for inputs existing within the fixed radial distance from the center of the kernel, and they are found to be radically symmetric, and hence the name radial basis function, because it is symmetric across the y-axis. The entire network forms a linear combination of the non-linear basis function, and the basis function in the hidden layer produces a significant non-zero response to the input stimulus that it has received only when the input of it falls within a small localized region of the input space. So this network can also be called as the localized receptive field network. So if you see on the screen, the architecture looks like this. We have three layers: input, output, and hidden layer. So n number of neurons in the input layer, m number of neurons in the hidden layer, and k number of neurons in the output layer. we have two sets of weights, weight matrix V and weight matrix W. Both these matrices are updated during the training process. So let us see the training algorithm of RBF. So first of all, set the weights to small random values, then perform steps 2 to 8 till stopping condition becomes true. Then perform steps 3 to 7 for each input. So each input unit xi for all I is equal to 1 to n receives input signals and transmits to the next hidden layer unit. Then calculate the radial basis function using that formula which I just showed. Then select the centers for the radial basis function. Then the centers are selected from the set of input vectors. It should be noted that a sufficient number of centers are selected to ensure adequate sampling of the input vector space. Then calculate the output from the hidden layer unit. So Vixi is equal to e to the power minus summation j is equal to 1 to r xji minus xji cap. So this you divide by sigma I square, where xgi cap is the center of the RBF unit for input vectors, and sigma I is the width of the ith RBF. So xgi is the jth variable of input pattern. Then you calculate the output of the neural network. So ynet is equal to w naught plus summation I is equal to 1 to k wim vixi. So where k is the number of hidden layer nodes, that is your RBF function, and ynet is the output value of the mth node in the output layer. Wim is the weight between the RBF unit and the mth output node, and w0 is the bias of the mth output node. Then you calculate the error and test for the stopping condition. Now you can choose any stopping condition. It may be some sufficient number of epochs or maybe to a certain extent of weight change. So we have discussed several supervised learning networks like perceptron, Adeline, Medline, backpropagation, and radial basis functions. So these are some of the most popular neural networks that are used. However, other neural networks are also there, whose details we will not be covering. We will now be discussing associative memory neural networks. So as I told you yesterday, that associative memory neural networks are mainly used to associate two types of information. So for example, you have various senses, right? You have the seeing sense, smelling sense, hearing sense, and you associate some data with each information that you sense. For example, you see the image of a rose and you associate the term rose with it, right? You see image of an object, say a bag, you associate the term bag with it. Similarly, you hear any sound, right? You hear any speech and you associate some term. For example, you hear the voice of your friend and you immediately recognize that this person is XYZ, right? So this is like associating one type of information with another type of information. That is the ability to learn and remember unrelated items, right? So the same thing has been emulated, same capability of human brain has been emulated in the form of associative memory networks. So this is defined as the ability to learn and remember the relationship between unrelated items. So for example, remembering the name of someone or the aroma of a particular perfume, right? So this deals specifically with the relationship between different objects or concepts, and a normal associative memory task, it involves testing participants on their recall of pairs of unrelated items, maybe face name pair. So for example, you input some face image and you want to get the name of that person as output, right? So this is just like associating two different unrelated items, and
storing them so that you can recall them at a later point of time. So for this, you are using associative memory neural networks. So these networks are used for modeling and learning and retrieving the memories in the brain. So retrieved memory and its query are typically represented by binary, bipolar, and real vectors describing patterns of neural activity. So learning is the process of forming associations between related patterns. Now, these patterns that we associate may be of the same type or may be of different types. Like you can have image of the same person, right? From the front view, little bit changing to the left, little bit changing to the right. So it may be of the same type or it may be of different type. Like you have the image and the name pair, right? So these associations can be either of the same type or of different type. So each association is an input-output vector pair, that is S colon T. So if each vector T is the same as the vector S with which it is associated, then the net is called auto-associative memory. So this means that input and the output vectors are the same. Then such networks are called auto-associative memory. But if the T's, that is the outputs, are different from the inputs, right? If the T's are different from S's, then the net is called a heteroassociative memory network. In each of these cases, the net not only learns the specific pattern pairs that were used for training, but also is able to recall the desired response pattern when given an input stimulus that is similar or may not be identical to the training input. That means they are able to tolerate noise and missing values also up to some extent. Now let us see the training algorithm for pattern association. So two algorithms are there. One is Hebb's rule, another is outer product rule. So in Hebb's rule, this is used for finding the weights of an associative memory, and training vector pairs are denoted by S colon T. So let us see what is Hebb's rule. So first of all, you initialize the weights to 0. So all the weights you set as Wij is equal to 0. Then for each training target input-output vector, that is S colon T, you perform steps 2 to 4. Activate the input layer for the input training vector, that is Xi is equal to Si. Then activate the output layer for the target output, that is Wj is equal to Tj. You are simply applying the input vector at the input layer and the output vector at the output layer. Simple. Then you start the weight adjustment. So Wij new is equal to Wij old plus Xi. That is, you are simply changing the weights by the product of the input and output. This is your Hebb rule, that delta W is equal to the product of input-output vector. So this is used with patterns that can be represented as either binary or bipolar vector, right? So a flowchart to represent the same algorithm has been shown on the screen. That is, you initialize first of all the weights to 0, and then for each input-output vector pair, you apply the input at the input layer, output at the output layer, and then you calculate the change in weight by simply taking their product x into y. So similar to the Hebbian learning for classification, we have bipolar or binary patterns. So for each training sample S colon T, delta Wij is equal to Si into Tj. So delta Wij increases if both Si and Tj are increasing. So they are on or binary and have the same sign in case of bipolar. So Wij is equal to summation P is equal to 1 to P, SIP into TJP. So this W, capital W, actually represents the weight matrix. So instead of obtaining W by iterative updates, it can be computed from the training set by calculating the outer product of S and T. That is simply taking a matrix multiplication of the input and the output vectors. So this is called the outer product rule. So let S and T be row vectors, Then for a particular training pair, ST, you have S1, S2 and so on up till Sn, and T1, T2 and so on up till Tm. You simply take a multiplication of these vectors, so you get the weight matrix. So suppose you have to write a code for this thing. You will be writing 3 nested loops, right? For P, I and J. So let P is equal to 1 to P, that is the total number of patterns that are there. I is equal to 1 to N for every row in W, and J is equal to 1 to M for every element J in row I. In its original form, the delta rule assumed that the activation function for the output unit was the identity function. So delta Wij is equal to alpha Tj minus Yj into Xi, and a simple extension allows for the use of any differentiable activation function. So we just call this extended delta rule. So in this existing equation, you add another term, that is the f dash yinj, that is the first order differential of your activation function. So the delta wij now becomes equal to alpha tj minus yj xi into f dash yinj. So this is your delta rule. So there are two rules, outer product rule and delta rule to calculate the change in weight. Now let us see the auto-associative memory network. In auto-associative memory network, we have same number of neurons both in the input and the output layer. So here on the screen we can see n number of neurons in the input layer and n number of neurons in the output layer. So because training input and output vectors are the same, so determination of weights. So when you do the training process, this is actually called storing of vectors. So diagonal weight is set to 0 because you see that there are no interconnections between the nodes, self connections I should say. The nodes are not self connected. So the diagonal weights are 0 in the weight matrix. This is done to increase the net's ability to generalize over unknown patterns also. So the figure on the screen, this shows the architecture of the auto-associative memory network. Let us see the training algorithm of the auto-associative memory. So you initialize the weights to 0. So Wij is equal to 0, I is equal to 1 to n, and j is equal to 1 to n. Then in step 1, for each of the vector that has to be stored, you perform steps 2 to 4, and then you activate the input layer for training input, that is xi is equal to si, and you activate the output layer also with the target output, that is yj is equal to sj. Then you simply find out the weights by multiplying the input vector with the output vector, because that is your delta w. So W is equal to simply summation P is equal to 1 to P. So total capital P is the total number of patterns. S transpose P into SP, because here the target is also equal to S, right? Output is equal to input, right? So S transpose P into SP. So this is the testing algorithm. So this can be used to determine whether the given vector is a known or unknown vector. So I told you that in auto-associative memory, when you are performing the training, you are actually storing the P number of vectors, right? You are actually storing P input-output associations in the auto-associative network. Now in the testing phase, you will be checking whether a particular vector has been stored earlier or not. That is, it is known or not. So as net is set to recognize a known vector, if the net produces a pattern of activation on the output which is same as the one stored, right? So this means that because it is auto-associative, the output should be equal to the input, right? So if you are inputting any vector, then as the output you should get the same vector, then this means the vector is known. So whatever weights you obtained in the training process, you set the weights as the initial weights of the network. Then for each testing input vector, perform steps 2 to 4. Then activation of the inputs is equal to the input vector. And you calculate the net input for each output unit. That is Yij is equal to summation I is equal to 1 to n xi wij. Then you calculate the output by applying the activation vector over the net input. So yi is equal to f by ij is equal to 1 if yij is greater than 0 and minus 1 if yij is less than equal to 0. So for an auto-associative net, the training input and target output vectors are identical. So the process of training is called the storing of the vectors. Now these vectors can be binary or bipolar. The performance of the net is judged by its ability to reproduce a stored pattern from noisy input, and performance is in general better for bipolar vectors than for binary vectors. So auto-associative networks are quite similar to hetero-associative networks, with the difference that target input and output, right? Input and target output is same in auto-associative networks. So TP is equal to SP, and this is used to recall a pattern by its noisy or incomplete version. So pattern completion or pattern recovery. A single pattern S is equal to say 1 1 1 minus 1 is stored. Weights are computed by Hebbian rule or outer product. So W is, so this is the W, right? So say you have a training pattern 1 1 1 minus 1, right? And by Hebbian rule you have obtained this weight matrix W. Then how will you check that whether this pattern is known pattern or not? You simply multiply this pattern with W. So you will get 4 4 4 minus 4, and then you apply the activation function. So you remember the activation function is this one. That is, you get 1 if yinj is greater than 0 and minus 1 if yinj is less than equal to 0. Okay, so you apply this activation function. Since all the values are greater than 0, so you get 1, and minus 4 is less than 0, so you get minus 1. So 1 1 1 minus 1. Now you see that this is equal to the input pattern that you had taken, 1 1 1 minus 1. So this means that this pattern is known. Now suppose you want to introduce some noise in this pattern. So you change the first value, you reverse the sign of the first value. That is, you make 1 as minus 1. So minus 1, 1, 1, minus 1. And then you again multiply it by W. And you get 2, 2, 2 minus 2. Now you apply the activation function. So for all the positive values, you get 1. For the negative value, you get minus 1. So 1, 1, 1, minus 1. So this means that even if one value is, or sign is reversed, that is, noise has been added, still it is recognizing the input value. Now suppose some values are missing. Say we make the first two values as 0, right? So we have the input vector as 0, 0, 1, minus 1. Now we want to check whether this is known or not. So we multiply it by the weight matrix. We get 2, 2, 2, minus 2, and we apply the activation function. So 1, 1, 1, minus 1. Now this is again the same as the known vector. So till 2 missing values, it is giving you the correct result. So it is robust up till 2 missing values and is robust up till 1 noisy value. Suppose you increase the noise. Now you change the sign of 2 values. That is, first 2 values, you make them minus 1, minus 1. So now the input vector is minus 1, minus 1, 1, minus 1. and now you apply it by the weight matrix, you get 0, 0, 0, 0. And if you apply the activation function over this, you will again get 0, 0, 0, 0. So this is not recognized. Why? Because this is not equal to the input vector that you are having, right? So this means that it is not robust to two noisy values. However, it is robust up till one noisy value and two missing values. So this process of using the net can be written like this, that you multiply the input vector with the weight matrix, you get some value that is 4, 4, 4 minus 4, and then you apply the activation function to get the final value that is 1, 1, 1 minus 1, which is same as the input value. So as before, the differences take one of the two forms. That is mistakes in the data or missing data. So mistakes are represented, or noise are represented by changing the sign, and missing data is represented by making the value as 0. Now in some cases, the net may not give you the correct output in one go, in one iteration, right? So in that case, you may require multiple iterations of the auto-associative memory network. Such networks are called iterative auto-associative memory network, right? So testing a recurrent auto-associative net, you get the stored vector in maybe second or third or fourth iteration. Okay. So suppose the weight matrix to store the vector 1, 1, 1 minus 1 is this, right? This is the weight matrix that you have obtained after completing the training process. Now let us do the checking of this network that we have obtained. So the vector 1, 0, 0, 0 is an example of a vector formed from the stored vector with three missing components, right? So if you see the stored vector is 1, 1, 1 minus 1. Now if you make three values as missing, last three values, it will become 1, 0, 0, 0. So let us see whether our network is able to identify this vector. So when the input vector is 1, 0, 0, 0, we multiply it by the weight matrix. We get 0, 1, 1, 1, 0, 1, 1 minus 1, which is not a known vector. So we again iterate. We input this vector again into the network. That is, multiply this vector with the weight matrix again. So we multiply 0, 1, 1 minus 1 with the weight matrix. To get 3, 2, 2 minus 2, we will apply the activation function to get 1, 1, 1 minus 1. Now this is known vector. This is same as the vector which was stored in this network. So for the input vector 1, 0, 0, 0, the net produces the known vector as the response in two iterations, right? So this iterative auto-associative memory network is working, and in multiple iterations it is able to recognize the known value. Another type of associative memory network is your hetero-associative memory network. Now in this case, the output is not same as the input, right? So you have different number of neurons in the output layer and different number of neurons in the input layer. So if you see the architecture of this hetero-associative memory network on the screen, you have n number of neurons in the input layer and m number of neurons in the output layer with weight interconnections. Now determination of weight can be done by Hebb rule or delta rule. Both the rules we have seen. Let us see. So training part is same. Training process is same of this hetero-associative network as auto-associative network. So we are skipping that. We will straight away come to the testing part of the algorithm. So you initialize the weights from the training algorithm. Then you perform steps 2 to 4 for each input vector. Then set the activation inputs equal to the current input vector given xi. Then you calculate the net input to the output units and determine the activation of the output units over the net input. So yinj is equal to summation I is equal to 1 to n xi wij, and your activation function is 1 if yinj is greater than 0, minus 1 if yinj is less than 0, and is equal to 0 if yinj is equal to 0. So the output vector y obtained gives the pattern associated with the input vector s. Now, if the responses are binary, then the activation function is like this. That is, yj is 1 if yinj is greater than 0, and is 0 if yinj is less than 0. So, associative memory, this is just a quick summarization of whatever we have studied. So they are nets in which weights are determined in such a way that a net can store a set of P pattern associations. So each association is a pair of vector SP and TP, where P is the total number of patterns. So each vector SP is an n tuple that has n components, and each TP is an m tuple. So the weights can be found using the Hebb rule or the delta rule. So this is the architecture of the heteroassociative memory. You can see we have n number of neurons in the input layer, m number of neurons in the output layer, which are interconnected, and this is unidirectional. If you see, it is the arrows are pointing from x to y only, right? So it is unidirectional feed forward. So let us see an example of heteroassociative memory. The binary pattern pairs are S colon T. So suppose the length of S is 4, that is number of neurons in the input layer is 4, and length of S is T, length of T is 2, that is mod T is 2. So number of neurons in the output layer is 2. So total weighted input to output unit is equal to summation xi wij. So then you will simply apply activation function over this net input. So wj is equal to 1 if yinj is greater than 0, and 0 if yinj is less than 0. This is for binary data. So weights are computed by Hebbian rule. Sum of outer product of all training pairs. So W is equal to summation P is equal to 1 to P SIT into TJ. So suppose the training samples are like this: 1 0 0 0, 1 1 0 0, 0 0 0 1, and 0 0 1 1. These are the input vectors, and corresponding output vectors are 1 0 1 0, 0 1 0 1. Right? So this means that we have 4 patterns, right? Capital P is equal to 4. Now, in this, first of all, we will calculate so let us do the training of the network first of all. So we will calculate the weight matrix using the outer product rule. So you simply do the matrix multiplication of the input and output vectors. So by taking the matrix multiplication, you get the weight matrix. This is your weight matrix that you have obtained. Now let us recall. Let us see whether the values are getting recalled or not. So suppose we want to recall 1 0 0 0. Now if you see here in the input pattern, 1 0 0 0 is actually your first known value, right? So that is your pattern 1. So this should give you a final class of 1 0. So when you multiply 1 0 0 0 with the weight matrix, you get 2 0, and when you apply the activation function, you get 1 0, which is your T1. Okay, so this pattern is being recalled, right? Another is 0 1 0 0. So if you see in the list of known patterns, your pattern 2, P2, is quite similar to 0, 1, 0, 0. Only the first value has been changed to 0. Right? So your output should be 1, 0. Now let us see whether we get 1, 0 or not. So we are simply multiplying this 0, 1, 0, 0 with the weight matrix. We get 1, 0. So this means again this vector has been recognized by our model. Now third value is 0, 1, 1, 0. So if you see in these known values, 0, 1, 1, 0 is not similar to any of these vectors. So whatever value you will get, it will be unknown. So you multiply by the weight matrix and you get 1, 1. Now this 1, 1 is an unknown class, right? So it is recognizing only the known vectors with 1 unit of missing value. Another type of associative memory network is bidirectional associative memory. So if you see on the screen, you have two layers, input and output layer. So X layer and Y layer. You have different number of neurons in each layer. So N number of neurons in input layer and M number of neurons in output layer, which are interconnected. And you see that these arrows are bidirectional. So this means that you can feed the input again at the Y layer to get the output at the X layer. You can go in both the directions in this case of network, and therefore they are known as bidirectional associative memory network. So this was developed by Costco in the year 1988, and it performs both backward and forward search. It encodes binary and bipolar pattern using the Hebbian learning rule. So they are of two types, discrete BAMs and continuous BAM. So weight matrix from X to Y is denoted as capital W, and weight matrix from Y to X is denoted as WT, because the values will remain the same. So we just take the transpose of that matrix. Now let us first of all see the discrete bidirectional auto-associative memory. So here the weight is found to be the sum of the outer product of bipolar form. So activation function is defined with non-zero threshold. Let us first of all see how to determine the weights. So input vector is denoted as SP and output vector is denoted as TP. So then weight matrix can be determined by using the Hebb rule. So if the input vector is binary, then the weight matrix is given by 2s of p minus 1 into 2 t of p minus 1. That means you are multiplying it by 2 and subtracting 1 so as to neutralize the zero value, right, in the binary data. However, if the data is bipolar, then you don't have to do this operation. You simply take the product of S and T, right? So the weight matrix in case of bipolar data is W is equal to summation P is equal to 1 to P SP into TP. So the weight matrix will be in bipolar form whether the input weights are binary or not, right? So in case of binary data, you multiply by 2 and subtract 1. So 2s minus 1 into 2t minus 1. This you are doing so that your final weight matrix is in bipolar form only and not in binary form. So let us see the activation function that you can choose for BAM. So this is based on whether the input target vector pair used are binary or bipolar. So the activation function for Y layer with binary input is Yj is equal to 1 if Yinj is greater than 0, and is Yj if Yinj is equal to 0, and 0 if Yinj is less than 0. However, for bipolar data, you have Yj is equal to 1 if Yinj is greater than theta, Yj if Yinj is equal to theta, and minus 1 if Yinj is less than theta. So the activation function for the X layer, with that is your input layer, with binary input vector is 1 if Xin is greater than 0. It is Xi if Xin is equal to 0, and 0 if In is less than 0. With bipolar input vector, you have xi is equal to 1 if xin is greater than theta. It is x if xin is equal to theta, and minus 1 if xin is less than theta. So if the threshold value is equal to the net input, then the previous output value is calculated, is left as the activation of that unit. So signals are sent only from one layer to the other and not in both the directions. So at one point of time, the signal will be sent in one direction only. Now training we have already seen. Now let us see the testing algorithm for discrete BAM. So you want to test the noisy patterns entering into the network. So the testing is algorithm looks like this. You initialize the weights to store P vectors, then initialize all the activations to 0. Then perform steps 2 to 6 for each testing input and set the activation of the input layer, that is X layer, to current input patterns, presenting the input X to the capital X layer and presenting the input Y to the Y layer. So it is bidirectional memory. So then you perform steps 4 to 6 when the activations are not converged. So you update the activation of units in Y layer. You simply multiply the input value to the weight vector. Then you apply the activation function over this. So you get Yj is equal to f of Yinj. Now you send the signal to X layer, and here you update the activation units in the X layer. So Xin is equal to summation j is equal to 1 to m Yj Wij. Then you apply the activation function over the net input. So Xi is equal to f of Xin. Then you send this signal to the Y layer. You test for convergence of the net. The convergence occurs if the activation vectors X and Y reach equilibrium. If this occurs, then you stop, else continue. Now let us see continuous BAM. Here the activation function that is used is a continuous function. So for example, you can use the logistic sigmoid function as the activation for all the units. So it may be binary sigmoid or bipolar sigmoid. Bipolar sigmoid function with high gain converges to vector state and acts like discrete BAM. So if the input vectors are binary, SP and TP, the weights are determined using this formula. Wij is equal to summation P is equal to 1 to P, 2S P in, minus 1 into 2 TJ minus 1. Right, so this we are converting the binary input and output into the bipolar form of weight matrix. However, if a binary logistic function is used, then activation function is f of Yinj is equal to 1 upon 1 plus e to the power minus Yinj. If the activation function is bipolar logistic function, then f of Yinj is equal to 2 upon 1 plus e to the power minus Yinj minus 1, that is equal to 1 minus e to the power minus Yinj upon 1 plus e to the power minus Yinj. So net input is calculated with bias included. So you simply add Bj into the summation of Xi Wij. So let us see the analysis of the Hamming distance and energy function. So Hamming distance is the number of mismatched components of two given binary or bipolar vector. So this is denoted as h of x dash. So suppose we want to calculate the average Hamming distance between two vectors x and y, right? So it is 1 0 1 0 1 1 0 and 1 1 1 1 0 0 1. So you see that these vectors differ at second bit, fourth bit, fifth, sixth, and seventh bit, right? So total 5 bits at 5 places they are different in their bits or values. So your Hamming distance is 5. And now if you want to calculate the average Hamming distance, you simply divide it by the total number of bits that are there in each vector, that is 7. So average is 5 by 7. Stability of this function is determined by the Lyapunov function, that is the energy function. So this Lyapunov function must always be bounded and decreasing. So you see that EFXY is always greater than equal to, that is, it is lower bounded, the summation of all the weight values. So the memory capacity is given by min of m comma n. So if you want to increase the memory capacity of your associative memory network, then you take more number of nodes in the input and your output layers. So this is a quick summary of bidirectional associative memory. It was proposed by Bart Kosko. It is hetero-associative in nature. It associates patterns in both the on both the sides, from set A to set B, and then again vice versa from set B to set A. It can also produce correct outputs despite corrupted or incomplete input. So it consists of two fully interconnected layers of processing elements, and can also be a feedback link connecting each node to itself. So this is a architecture of a typical BAM. We have n-dimensional input vector and n-dimensional output vector. So you see that it works in both the directions. So you can give the input towards the X side and obtain the output at the Y layer, and again give the output at the Y layer and get the input at the X layer, right? So this process is repeated till you get input and output vector as unchanged, right? So if you reach a stable state. So the basic idea behind BAM is you want to store pattern pairs so that when n-dimensional vector x from set A is presented as input, the BAM recalls the m-dimensional vector y from set B. And when y is presented as input, the BAM recalls x. So it means that recall should be on both the sides. So you input x, you should get y, and when you input y, you should get x. So this is the BAM training algorithm. With the help of an example, let us understand it. So first of all, we want to store say 4 pair of vectors. So we have 1 1 1 1 1 1. So 6 units in the input and 3 units in the output. Okay. So 6 neurons in the input layer and 3 neurons in the output layer. This will be the architecture, and you have 4 pair of patterns. Now in the training process, you will be calculating the weight matrix. So you simply take the outer product of the input and output vectors and you sum them all to get the final weight matrix. So this is your weight matrix that is obtained. Then you want to test your trained model. So BAM should be able to receive any vector from set A and retrieve the associated vector from set B, and receive any vector from set B and retrieve the associated vector from set A. So first we need to confirm that BAM is able to recall ym when presented with xm, right? So you will simply, to do this, you will simply multiply xm with the transpose of the weight matrix and then apply the activation function. So suppose you want to check for 1 1 1 1 1 1, that was your first vector. You multiply it by the weight matrix and then you apply the activation function. You get 1 1 1. And if you see in the input vectors, 1 1 1, that is y1, is your corresponding output for your x1. So this means that the model is correctly giving the output pattern for the input 1. So we confirm that BAM recalls xm when presented with ym. Now we will be doing vice versa. Suppose we present any value of y, we will be multiplying it by w, applying the activation function to see whether we get the corresponding pair of that y value. Okay, so suppose we take 1 minus 1 1 as the y value to check. We multiply by the weight matrix and apply the activation function. So we get this value 1 1 minus 1 minus 1 1 1. So if you see here, 1 minus 1 1, that is y3, you are getting corresponding x3, right? When you input y3, you get corresponding x3 as output. So this means that your model is giving you the correct value of x3 for inputted y3. Now let us see that if you present an unknown vector to the BAM and retrieve whether you are able to retrieve a stored association or not. So the probe presented may have corrupted or incomplete value of a pattern from set A or from set B stored in the BAM. So initialize the BAM retrieval algorithm by setting x0 is equal to x and calculate the BAM output at iteration p, that is you find out yp, and then update the input vector xp. So you repeat the iteration until equilibrium, then input and output vectors remain unchanged with further iterations. So the input and output patterns will then represent an associated pair. So this means that BAM is unconditionally stable and any set of associations can be learned without risk of instability. So this important quality arises from the BAM using the transpose relationship between weight matrices in forward and backward direction. So suppose we use vector x as a probe. So in this x we have changed the sign of the first value. Okay, so there is a single error in x1, right? So instead of 1 we have kept it minus 1. Now this probe is applied as the BAM input produces the output vector y1 from set B. So this vector y1 is then used as input to retrieve the vector x1 from set A. Suppose you apply this vector x into this trained model, you get y1 as the output. When you again apply y1 as input to this BAM, you will get x1. Now this x1 is a known vector. So this BAM is capable of error correction. As soon as you get x1, you are able to know that, okay, the first bit, the first value was changed. From 1, it was changed to minus 1. So this can even correct the errors. So this will be all. Now let us meet at 6 again. At 6 p.m. again, we will be joining. Okay, thank you all of you.
Okay.
Hello everyone. Anybody is there?
Yes, ma'am.
When the session will be getting started?
Within 10 minutes.
Okay, fine. I'm waiting that how and when. How are you, Ravi sir?
Fine, ma'am.
Thank you, sir. So you are there in the WhatsApp group?
Yes, ma'am.
Okay, fine, sir.
So hello everyone, welcome back. I will now be sharing my slides. Are the slides visible?
Yes, ma'am. It is visible.
Yes, ma'am.
Okay, thank you for your response. So let us start the off-field neural network. So this was developed in the year 1982, and Hopfield promoted the construction of the first analog VLSI network chip. So these are again of two types, just like BAMs, because BAMs are also of two types, discrete and continuous. Similarly, Hopfield network is also of two types, discrete and continuous. So discrete Hopfield network is an auto-associative, fully interconnected, single-layer feedback network, and it is symmetrically weighted network. So this is operated in discrete fashion. When it is operated in discrete fashion, it is called discrete Hopfield network, and its architecture is like a single-layer feedback network. That is a recurrent network. So two types of inputs can be used in this, like the binary and the bipolar. So typically bipolar inputs are mostly used. However, self connections are not there. So the diagonal of the weight matrix is always 0. So this weight matrix is actually a symmetric matrix. Wij is equal to Wji. Since the weights are symmetric, only one unit updates its activation at a particular point of time. An input pattern is applied to the network, and the network's output is initialized accordingly. So initialized pattern is removed and initialized output becomes new updated input through the feedback connections. So this process continues until no new updated responses are produced and the network reaches its equilibrium. So the asynchronous updation is called as the energy function of Lyapunov or the Lyapunov function, and the energy function proves that the net will converge to a stable set of activation. So this is the architecture of a discrete Hopfield network. So processing elements with two outputs, inverting and non-inverting. So outputs from each processing elements are fed back to the input of the other processing element and not to itself. So if you see that the Y1 node in the figure, an edge is coming out, which is actually going again as input to Y2, Y3, Y4, and so on, but not again to Y1, right? So self connections are not there. However, feedback is there, and therefore it is also known as a recurrent network. The connections are resistive, so no negative resistors. So excitatory connections use positive inputs and inhibitory use inverted inputs. Excitatory output is same as the input. So inhibitory input is different from the output. So weight is positive if both the units are on. If connection strength is negative, then one of the units is off and the weights are always kept symmetric. Let us see the training algorithm of discrete Hopfield network. So for storing a set of binary patterns, the weight matrix W is given as Wij is equal to 2Si P minus 1 into 2Sj P minus 1. So this we are doing to keep the weight matrix as bipolar. So for storing bipolar pattern, we will not be doing multiplication by 2. We will be simply taking the product of the input and the output. So Wij is equal to summation P is equal to 1 to P, SIP into SJP, and self connections are not there. So Wij is 0 when I is equal to J. Now let us test this algorithm. So we initialize the weights as the weights that we obtained from the training algorithm. So when the activations are not converged, perform steps 2 to 8. Then perform steps 3 to 7 for each input vector x. Make initial activation equal to external input vector x. So yi is equal to xi. Then perform steps 5 to 7 for each unit yi. Calculate the net input of the network, that is ymi is equal to xi plus summation over all j yjwji. Then apply the activation function over the net input to calculate the output. So yi is equal to 1 if ini is greater than theta. It is yi if ini is equal to theta, and is minus 1 if ini is less than theta. Then feedback the obtained output to all the other units and test the network for convergence. Only a single neural unit is allowed to update its output. Next update is carried on randomly on a randomly chosen node that has already updated output. So this is asynchronous stochastic recursion. If the input vector is unknown, the activation vectors resulted will converge into a pattern which is not in stored pattern. So such a pattern is called spurious stable state. Now let us see the analysis of energy function and storage capacity on discrete Hopfield net. So energy function is that function which is bounded and is non-increasing function of the state of the system. So Lyapunov function is used, which determines the stability property. So network is stable because energy function decreases whenever the state of any node changes. So assume node I changes its state. So a positive definite function E of Fy can be found such that E of Fy is continuous for all components yi, and def yt by dt is less than 0, that is the first order differential is less than 0, which indicates that the energy function is decreasing with time. The storage capacity is equal to 0.15 n, where n is the total number of neurons in the net. Then another one is your continuous Hopfield network. So they can be converted, the discrete can be converted to continuous if time is a continuous variable. So they are used in associative memory problems or traveling salesman problem. So nodes have continuous graded output and energy decreases continuously with time. So electronic circuit which uses non-linear amplifiers and resistors and are used in building Hopfield with VLSI technology. Then another one is your iterative auto-associative network. So this net does not respond to the input signal with the stored target pattern. So this responds to like a stored pattern. Like it should not be exactly the same as the stored pattern, but maybe quite similar to the stored pattern. And it uses the first response as input to the net again. So iterative auto-associative network recover original stored vector when presented with test vector close to it. And it is also known as recurrent auto-associative network because here the output that you get in one iteration, you use it as the input in another iteration. Another one is your linear auto-associative memory. So this was given by James Anderson in 1977 and is based on Hebbian rule. So linear algebra is used for analyzing the performance of the net, and stored vector is eigenvector. Eigenvalue is the number of times the vectors are presented. So when input vector is x, the output response is xw, where w is the weight matrix. So if AP is the input pattern, then AI AJ transpose is equal to 0 for I not equal to J. So summation AI square is equal to 1 for all P is equal to 1 to P, where P is the capital P is the total number of patterns. Then the output Yj is equal to AP. That is the desired output has been recorded. let us see what is deep learning. So deep learning is a subset of machine learning that is inspired by human brain. When I was giving you the introduction of neural network, I told you that entire concept of neural network is actually an effort to emulate the human brain. Now, deep learning is nothing else but another specialization of a neural network where number of hidden layers are increased, right? So in deep learning, the deep is actually the number of hidden layers that have been increased. So this uses a neural network with multiple layers, and that is why it is called the deep architecture or the deep neural network or deep learning. So it powers applications in AI such as image recognition and NLP. The main characteristics of deep learning architecture is that first of all they have multiple internal layers or hidden layers. Another thing is that deep learning architectures, mostly all of them take a lot of time. They are extremely complicated and are difficult to run on commodity hardware, and therefore you require special computers like GPUs and servers to run these algorithms and architectures. Examples of deep learning architectures are convolutional neural network, popularly known as CNN. Now, the CNN is mostly used for image processing, right? Image type of predictions, image segmentation, image cropping, image analysis, object recognition, and all that. Recurrent neural network is mostly used for predictions in time series data, like signal processing, speech recognition, and others. Another one is your generative adversarial network or GAN. This is used in case of data generation, like when you want to generate data of a similar type. For example, two similar images or two similar kind of videos, or to predict what will happen, what will be the next frame in a particular video, right? So for all these things, generative adversarial networks are used. And transformers, they are the state-of-the-art techniques in NLP, natural language processing. Now, first of all, let us see the convolutional neural networks that are the deep learning techniques for image and feature analysis. So convolutional neural networks, they are specialized deep learning models. They are ideal for image and video data analytics. They were actually proposed in first place for image processing only. The key role in computer vision tasks such as image classification, object detection, object recognition, image segmentation, right? All these things, in all these things, CNN is useful. So CNNs identify spatial hierarchies in data. They start with the low-level features, example edges, and progress to high-level features. So what they do is actually so one important thing about deep learning is that you don't have to extract the features and then give it to a deep learning model, just as you have to do in machine learning. In machine learning, you have to feed to the model the data set in the form of proper instances and features, right? However, you don't have to do it in deep learning. In deep learning, the internal or the hidden layers, they automatically extract the features, right? So here the CNN automatically extracts the features from the images, and it starts with low-level features like edges and corners and demarcation lines, and then progresses further to identify the high-level features. So this CNN processes data layer by layer to extract the meaningful pattern. So this is how the CNN architecture looks like. So we have an input layer, convolutional layer, max pooling layer, dense layer or fully connected layer, and finally the output layer. So input layer is the layer at which we provide the input in the form of images or a set of images. So this layer simply holds the raw input data. Then this layer provides the input to the convolutional layer. Now this convolutional layer is responsible to extract the features. It uses
multiple filters. So you can use any number of filters here to extract the features. And thereafter, once the features have been extracted, activation functions are used onto them to introduce non-linearity. Activation functions like rectified linear unit, they are introduced. They are used to introduce non-linearity. Non-linearity is essential in neural networks. Otherwise, they will just be able to classify data that is linearly separable. Even though whatsoever number of layers you use in a neural network, if you don't use an activation function, then it will simply act like a linear regression, right? It won't be able to classify data that is linearly inseparable. So its non-linear classification abilities come with the help of activation function only. So activation functions are extremely important in case of neural networks. Another is your pooling layer. So pooling layer reduces dimensionality while preserving features. So two types of pooling layers are there: max pooling and average pooling. Then once your dimensionality has been reduced, the output goes to the flattening layer. So the resulting feature maps are flattened into one-dimensional vector after the convolution and the pooling layers. Then it goes to fully connected layer or the dense layer. Now this dense layer actually maps the features to the output label. Thereafter, it goes to the output layer, and the output layer applies a activation function, like say a sigmoid logistic sigmoid function or a softmax function, to convert the output into the probability value for each class. So let us see the working of each layer in detail. So input layer is one where we give the input to the model. Input is an image or a sequence of images. And let us consider an image with width 32, height 32, and depth 3. We take depth 3 because we have RGB, right? 3 pixels. So depth third dimension is 3. Then we have the convolutional layer. So this layer is responsible to extract features from the input data and perform convolution operation to detect the patterns. So this consists of a set of learnable features, filters, or kernels having small width and height and the same depth as that of the input volume, that is 3, right? So the kernel will be having some smaller dimension, that is 2 cross 2 or 3 cross 3, 5 cross 5, or whatever you choose. So these filters or kernels, they extract specific features. They are actually rolled over the entire image over segment by segment, right? So you just slide.
Hello, ma'am. Am I audible, ma'am?
Yes.
Hello, ma'am.
Yes.
Ma'am, your slide, PPT slide screen is not visible, ma'am.
Oh, is it?
Yes, ma'am.
Wait, I will share again then. Is the slide visible now?
Not visible, ma'am. Ma'am, please ask some other participants. So it is not visible to me, ma'am.
Yes, it is visible. Maybe you can check your internet connectivity.
Okay. To others, is it visible?
Yes, visible.
Okay,
to
then I am rejoining. I think.
Jagat. Okay. So Mr. Jagat, kindly rejoin. I think there is some network issue on your side.
Yes, ma'am. Yes, ma'am. Ma'am, one more thing, ma'am. PPT slide is shareable, ma'am. Can you please provide after the end of the session?
Yeah. Slides, I think will be provided to you. Yeah.
Thank you, ma'am. Thank you. I am just leaving and rejoining, ma'am. Thank you.
Oh. Okay. So I was discussing filters. Am I audible, everyone?
Yes, ma'am, audible.
Okay. So I was discussing filters. So they are neural networks of a small size, like 2x2 or 3x3, and they are slided over the actual input image, and it computes the dot product between the kernel weight and the corresponding input image patch. So you can use any number of filters or kernels. So suppose you are using 12 filters for this layer, then you will get an output volume of dimension 32 cross 32 cross 12 because you have used 12 filters. Then stride. Stride is a parameter that will tell you that after how many pixels you should move your filter, right? So suppose your stride is 2, then you will move your filter after skipping 2 pixels. Then padding. So this maintains a spatial dimension. So padding is used to pad additional bits to a particular matrix so that your spatial dimension is maintained. Then activation layer. So activation function is important, and it is mostly used at the output level and at the pooling level. So this is a mathematical function applied to the output of a neuron, and it introduces non-linearity into the model, allowing the network to learn and represent complex patterns in the data. So without activation function, the entire network would behave like a single linear transformation, limiting its ability to model just complex relationships, right? So activation function is extremely important at this point. Linear activation function can also be used, but it is used for mostly linearly separable data. So generally, non-linear activation functions are used. Many non-linear activation functions we already discussed in yesterday's class. For example, different types of sigmoid functions. So which is defined by this equation: a is equal to 1 upon 1 plus e to the power minus x. And tan h, so this is a shifted version of sigmoid, allowing it to stretch across the y-axis. So again, it has the same shape, S shape. However, it is little bit shifted along the x-axis. So this is defined as 2 upon 1 plus e to the power minus 2x and minus 1. Then you have ReLU, that is rectified linear unit. It is defined by Ax is equal to max of 0 and x. So this means that if the input x is positive, the ReLU returns x, and if the input is negative, it returns 0. Now, why this is important? This is important because it is computationally less expensive than tan h and sigmoid. So it makes your model a little bit faster as compared to other activation functions. Now this sigmoid activation function is characterized by S shape, and it is defined as a is equal to 1 upon e to the power minus x, and this means that this curve is actually in the shape of S, smooth and continuous output. It allows neural networks to handle and model complex patterns that linear equations cannot. So the output ranges between 0 and 1, and therefore it is useful for binary classification. This function exhibits a steep gradient when x values are between -2 and 2. So this sensitivity is extremely important because this means that small changes in input can cause significant changes in the output, which is critical during the training process. Then another activation function, tan h or hyperbolic tangent function, is the graph is shown on the screen. It is also the S-shaped graph. It is little bit shifted as compared to the sigmoid one.
The output values range from -1 to 1. And it enables modeling of complex data patterns by introducing non-linearity. And this is commonly used in the hidden layers due to its zero-centered output, facilitating easier learning for subsequent layers. Then another one is your ReLU, that is rectified linear unit function. It is defined as AX is equal to max of 0, comma X. And value ranges from 0 to infinity. So whatever is the value of X, that will be outputted unless it is negative. If it is negative, then the value outputted is 0. So it is a non-linear activation function, allowing neural networks to learn complex patterns and making backpropagation more efficient. It has advantages over other activations. First of all, it is computationally less expensive than tanh and sigmoid, because here we have a simpler mathematical operation. And at a time, only a few neurons are activated, making the network sparse, making it efficient and easy for computation. Next is your pooling layer. Now, pooling layer, so in the convolutional layer, you have actually extracted all the features. Okay, and after that, you have applied the activation function. Now, you want to reduce the dimensionality so as to make your model computationally efficient. Okay, so two types of pooling can be done. One is max pooling and another is average pooling. Now, this max pooling selects maximum value in the region of the feature map covered by the filter. Okay, so suppose your filter is 2 cross 2, right? So it will take a matrix of 2 cross 2 in every iteration to cover the entire, till it covers the entire image, and then it will find out the maximum value in the region. So if you see on the screen, the first image shows the max pool. So here your filter is 2 cross 2, right? So, and stride is 2, right? So that means you will be shifting by 2 pixels. Okay. So if you see the first block of 2 cross 2, here you have values 2, 2 and 9, 4. Now, since this is max pooling, in each section you will be taking only the maximum value. Okay. So in the first section 2, 2, 9, 4, the maximum value is 9. Okay. So you will take the value 9. Then in the second section, which is shown by green, you have 7, 3, 6, 1, right? So the maximum value is 7 over here. So you will take the value 7 in the output. Then in the next section, which is shown by yellow, you have 8, 5, 3, 1. So maximum value is 8. So you will take 8 in the output. Then in the next section shown by red, you have 2, 4, 2, 6. So maximum value here is 6. So you will take 6 in the final output. So that is your max pooling. Then you will slide your filter to the next you can say column, and this you keep on doing till you cover the entire image. This is your max pooling. So what it does is it takes the most prominent features into consideration and leaves the other features. In average pooling, this computes the average value in the region of the feature map covered by the filter. So it gives the average of the features present in a patch. Okay. So if you see in this image that is at the bottom, you have this section of 2 cross 2 that is blue in color. So here you have values 2, 2, 9, 4. So instead of taking maximum value, you take the average of this one. So the sum of 9 plus 2 plus 2 plus 4 is 17. Okay, and then you take the average, that is divided by 4. So you will get 4.25. Similarly, for other sections also, you take the average of all the values, right, to get the final output. So this helps prevent overfitting and reduces computation. The advantages of pooling layers are multiple. First of all, it reduces the dimensionality. So each section also, if you take filter of 2 cross 2, each section of 4 cells is reduced into 1 cell, right? So it is very it makes it more computationally efficient, and it is also translation invariant. So suppose in your image your object translates to other position, it will not matter. The pooling layer will be invariant to that, and it is also actually doing feature selection. So it is leaving out the irrelevant or less important features and taking out the important ones. The disadvantages of pooling layer is information loss. For example, in max pooling, you take only the maximum value, so you take only the most prominent features and leave out the other ones. So you take only the prominent features like edges and corners and sharp lines, and you leave out the other less important ones. So some information is getting lost, uh, uh, which might create difficulty in image segmentation at a later stage. Then another is over smoothing. By taking just the prominent features, the detailed things present in the image, they get lost. And hyperparameter tuning. So what exactly should be the value of the stride? What should be the value of the filter? It becomes a matter of optimization, because you don't know that what size of filter and what size of stride is going to give you the best results. Then you have the fully connected layer. So in this layer, every neuron in the previous layer is connected to every neuron is in the current layer. So it uses features extracted by convolutional layers and pooling layers to determine the class scores or regression values. So this actually does the classification task. So for classification, the final fully connected layer uses a softmax activation to output the probabilities. The softmax activation function looks like this. Sigma z is equal to e to the power zi upon summation j is equal to 1 to k e to the power zj. So here sigma is your softmax value and z is your input vector. EZI is the standard exponential function for input vector, and EZJ is the standard exponential function for the output vector. The K is the number of classes in the multi-class classifier. So there are multiple applications of these CNNs. Most importantly, they are used in image-related tasks like image segmentation, image classification, object detection, object recognition, and so on. In natural language processing tasks like text classification, sentiment analysis, and even in healthcare domain like medical image analysis, diagnosing from the scans, or segmenting the problematic area in a particular image, and so on. They have multiple advantages, they do automated feature extraction, which would rather be a very difficult task if it were to be done manually. Then it has high accuracy in image and video analysis tasks. Limitations are also there. It is computationally expensive, so it requires costly resources like GPUs for execution, and it requires large data sets for training. Also, sometimes it may take a lot of time to process the entire data set, maybe some days or even a month. So CNNs are powerful tools for feature extraction and image analysis. Their hierarchical approach enables robust pattern recognition, and future advancements will broaden their applications in AI. Now let us see another algorithm in deep learning, that is your generative adversarial networks, that is GANs. So these GANs are a type of neural network that are used for generative tasks, right? For example, you have one image and you want to generate a similar image, or you have a video and you want to generate the next frames in that video, right? So for all these kind of generative tasks, GANs are used. So they were introduced by Jan Goodfellow in 2014, and it comprises of two neural networks. One is known as the generator and another is known as the discriminator, and they compete in a zero-sum game. So generator creates fake data samples, which are quite similar to the actual image, right? And the discriminator evaluates whether a sample that it is getting is real or fake. So the two networks they are trained simultaneously and they improve each other's performance. So they are actually contesting. The generator is trying to make as similar samples as possible, and the discriminator is trying its best to discriminate between the actual sample and the fake samples that have been generated by the generator. The algorithm ceases to train when the discriminator is not able to discriminate between the fake and real samples, right? At that time, the algorithm stops. So the generator takes, how the generator generates, it takes some random noise as input and generates data samples which are quite similar to the actual image or data that it has received. Then these samples along with the real samples, they are sent to the discriminator. The discriminator distinguishes between the real and fake data. So this is the type of adversarial training in which the generator is trying to fool the discriminator by creating similar samples, and discriminator tries to identify the real and fake as close as possible. So in the training process, the generator generates fake samples and the discriminator evaluates these samples alongside real data. The generator improves by minimizing the discriminator's success. The training continues until the discriminator cannot distinguish the real data points from the fake data points. So this finds application in image generation, like creating realistic images, and art generation, data augmentation, generating a new training data, super resolution, that is enhancing image quality, even to change black and white videos into colored videos, video prediction, like forecasting future video frames and so on. Training in these are the challenges of these GANs. One is training instability. So balancing the generator and discriminator is rather difficult. And mode collapse, the generator produces limited variations. So it is quite likely that it becomes in the game the discriminator wins very easily, and it requires large computation resources for training. So huge data set is required. As huge the data set will be, the more and more close image will be generated. Then there are multiple variants of GANs. One is DC GAN, that is deep convolutional GAN. This is for image related tasks, object recognition and so on. The cycle GAN translates the images between domains. Example, style transfer. And style GAN generates high quality images with controllable features. This again has multiple advantages and limitations. Advantage is that it generates realistic data points and versatile applications in multiple domains. And limitations are that it is computationally expensive and sensitive to hyperparameter tuning. So GAN is a powerful tool for generative tasks in AI, and their adversarial framework fosters innovative applications. So despite challenges, advancements continue to expand their potential. Another one is your recurrent neural network. So recurrent neural network, there are type of neural network designed for sequential data or the time series data. For example, your EEG signals, EMG signals, your speech recognition task. Okay, so for all these things, RNNs are used. Text to speech time series data. So key feature is the ability to retain information through hidden states. So RNNs process input data sequentially, maintaining a memory of the previous input. So whatever was the activation state at time t minus 1, it is passed on to the hidden state at time t, and which is again passed on to hidden state at time t plus 1. So hidden states pass information from one step to the next. So this enables context-aware predictions for sequential tasks. So as you can see in the figure, H is the hidden state, right? And X is your input, Y is your output. So WXH is your weight for the WXH is your weight between the input and the hidden state, and WHY is your weight between the hidden state and your output. And then there are self connections also. So that the hidden state is remains intact to be passed on to the next timestamp. So you see that in the figure, hidden state from timestamp t minus 1 is passed on to timestamp t, which is further passed on to timestamp t plus 1. So we have input layer which processes sequential data. We have hidden layer that maintains memory through hidden state, and we have output layer that produces prediction for each timestamp. Right. So we have so many RNN units, recurrent units, as we have the timestamps. So recurrence is there, so looping connections are there in the hidden layer. The main challenges in this are the vanishing gradient problem. So that is the difficulty in long-term dependencies, and exploding gradient problem, that is the unstable gradients during the training process. So these exploding gradients don't allow the network to converge or come to a optimal solution. So solutions to these problems include advanced architectures like LSTM and GRU, that is the graded recurrent units. So in long short-term memory, LSTM, this addresses vanishing gradients by introducing new memory cells, and gated recurrent units, it simplifies LSTM structure while maintaining the performance. And bidirectional RNNs, they combine forward and backward context, and they find applications in multiple domains like NLP, speech recognition, time series analysis, and so on. They have multiple advantages, like they are effective for sequential and temporal data, and it handles variable length input. And generally, the data set that it handles has a huge dimension. So they generally take a lot of time. So that is one of the main limitations. They are computationally intensive for long sequences and require especially a special type of hardware. And they are prone to vanishing or exploding gradients problem. Okay, so these are some advanced concepts. This is the conclusion. The popular frameworks are PyTorch. If you are good in Python, then you should use the PyTorch that has dynamic computation graphs and is more research friendly. Other framework are the TensorFlow, that is scalable for production, supports deployment, and another one is your Keras, that has high level application programming interface and is more user friendly. So these are widely used in academia and industry. Then we have supporting libraries like NumPy, which is efficient for numerical computations, Pandas, that is for data manipulation and pre-processing, Matplotlib for data visualization, and essential for data science workflows. So PyTorch, in PyTorch we have data preparation first of all, then model definition, and then you train the loop through forward pass, compute the loss, and then you back propagate. They have multiple applications in deep learning like computer vision, natural language processing, healthcare, and robotics. These are the challenges. First of all, they require a large amount of data. If you provide it a small data, then it will be overfitted and it won't give you generalized results. So it requires a large amount of data. The more data it gets, the better precision it makes. but it is very computationally costly. It requires efficient hardware, and it is always at the risk of overfitting, and there is lack of interpretability. So it is like a black box, and it is difficult to identify how a particular network has reached a particular solution. So deep learning, though, is revolutionizing various industries, it is still having its own glitches, and powerful frameworks and libraries have been proposed for this domain, but challenges are still there. So thank you so much. If you have any questions, you can ask.
Thank you, ma'am. Although you have covered very, wider aspect of deep learning and related to even GAN, also generative adversarial network, along with the activation functions and all. Ma'am, have you worked in the area of deep fake detection using this GAN and all? Any paper you have published?
No, using GAN we have not published. However, we have used autoencoders.
Autoencoder. So, ma'am,
Yeah, we have a paper published in autoencoders. Yeah.
Ma'am, I'm working in the area of deep fake detection, but I'm facing a lot of challenges. Can you guide me how I should proceed towards writing doing some significant work towards deep fake detection?
Towards what detection?
Deep fake detection.
Deep
Yeah.
deep detection.
Yes.
Okay. So what is the technique that you are using?
Basically, the way you have mentioned that in GAN, there are two optimization functions. One is generating the image, and another one is discriminating. Generator is generating an image so that discriminator cannot discriminate. So in deep fake, what we have to do, if the video is fake, so our model should detect whether this video is fake or not, whether this image is fake or not. Like you have to heard about the Obama, Mr. Obama case, or maybe Rashmika Mandana case. Deep fake were created, and it was recently it was in news. So with that perspective.
Okay, so you have applied GAN for this application, and is it giving you better results than state of the art?
I have tested just sample codes for GAN and style GANs, C GAN and all, but facing the challenges like let's say efficiency is very low. Maybe images are being generated that are not that much having low resolution and very away from the real images. Easily it can be distinguished that it is not close to the real one.
Okay.
Are you getting the point? What I
think you need a better parameter tuning technique. The parameters are not properly tuned.
Okay. So parameters will be one of the factor, right? Any suggestion for the resources so that we can get some better idea about it?
Okay, so first of all, image processing is not my research domain. I have used autoencoders in signal processing, but still I can think that it will be good if you can use some machine learning techniques for parameter optimization, maybe grid search or Bayesian technique. And you can also maybe if you are using images, you can pre-process the image in some way so that you may get some better results. First of all, pre-process and then you feed it into the GAN.
Okay, ma'am. Basically, you are from computer science or electronic background, madam?
I am from computer science, and I work in the area of applications of machine and deep learning. So I have worked in signal processing like handwritten character recognition and the different types of like we have Indian Sign Language, American Sign Language. So how to detect those signs that we make by forming the hand gestures. So this I have done not using image processing, but by using signals, that is wearing a band which is having some sensors, and the signals are generated, and then we train the models to identify that which character or which sign was formed using the hand gestures.
Okay. Thank you, ma'am.
Okay, most welcome. Is there any other question? Okay, thank you all of you. It was really nice talking to you all. And you have my mail ID on my homepage. So you can contact me through email anytime if you want for collaboration or any other suggestion. So thank you all of you for attending these lectures, and see you all.
Thank you, ma'am.
Ma'am, please, ma'am, how can I get the PPT materials, ma'am?
I will give it to the office. I think you can get it from the office, the TLC office, through which you have joined.
Okay.
Yeah.
Okay, thank you.
Okay, thank you all of you. See you all. Bye.